So if everything goes well, my plan is to be in here regularly. I'm hoping. And so far, everything looks like it's going really well. Kind of hard for me to see the screen right here, but let's click on here. Okay. So today's point is to sort of go back and pick up some of the pieces that we skipped over in order to talk about conservation momentum before the experiment of this week. And so I want to go back and just remind ourselves of there's two big results that we're using in this chapter. And that's kind of nice after chapter 6, maybe. One is the impulse momentum theorem that says, remember, the impulse is a vector. It's delivered to an object. So you have to define what your object is. And the impulse has x, y, and z components. The x component is that force's x component times the amount of time it acts for on the object. And the impulse momentum theorem concerns the net impulse given to an object. And it says it's equal to the change in momentum of the object, which is the momentum is nothing other than mv. So it seems simple enough. I mean, I know the impulse part sounds very unfamiliar because we don't use that word in everyday language, but hey, momentum is just almost the same thing as velocity. So it seems like you would have really good intuition about it. So we're going to do a few voting questions just to kind of check that. And I put the impulse momentum theorem down there for reference in these voting questions, just so that you could inspect it because it's been a while. Two different gliding carts. One's mass is double the other one. They're at rest on these frictionless tracks. If you push one cart for 3 seconds and then you push the other one for the same length of time and you exert the same force on each one, how, initial is when they're at rest and final is after the 3-second push time. How does the light cart compare to the speed of the heavy cart? Pushing with the same force, same amount of time, both starting from rest. All right, let's see a vote. If you got a vote, you can hold up fingers if you don't have yours. I'm seeing A's, B's, and C's in the room. For a second ago, I remember one of these was slightly more preponderous than the other one. And there are a couple B's thrown in too. Anybody want to help me think about this? We actually could have done this kind of voting question before we ever talked about the impulse momentum theorem, but we certainly can use the impulse momentum theorem. And is anybody thinking of it in terms of what's in this box down here? Newcomb, you want to help us? Yes. Right, so this goes away in the impulse momentum theorem. Yep. Yes. Right, so Newcomb is saying, let's apply this to the smaller cart and the larger cart. The left-hand side is the same for each cart, right? Now, really, there's 3 forces on the cart, right? The cart's riding on a frictionless track. There's a normal force, there's a weight force, but those cancel out in the net force because they're the only 2 vertical component forces. And then there's this horizontal push force that you're doing along the track. And so the net force is really just the push force because the other 2 forces cancel out. That's the same, we're told, in the text. And the amount of time they're pushed for is the same. So for the 2 carts, this side is the same. And as Newcomb said, this is 0. The initial speed is 0. So the final speed is something that's the same divided by m. And so the one that has the smaller mass is going to have the larger velocity, right? Smaller mass one is going to have the larger velocity. So the speed of the light cart is actually larger than the speed of the heavy cart. You could have figured that with acceleration too, right? F equals ma. The F is the same. The one that has the smaller m is going to have the bigger a just by dividing it out. Okay, the point of that was kind of a lead in to thinking about their momentum, because this at least uses our new definition. Same setup, pushing both, same force, both for 3 seconds. How does the momentum in the final state compare of the light cart compared to the heavy cart? Let's see a vote if you got it. It's almost the same question, so I'm assuming it doesn't take too much extra thought. Just looking for, I'm seeing B's and C's, either twice or equal to. Anybody feel strongly about one of those and want to explain it? Yes, Edward. Well, if the mass is twice as big, it won't be moving twice as fast, it will be moving half as fast. And when you multiply twice the mass times half the speed, you get the same. Although you could really just think of this as final momentum minus initial momentum. And again, the initial momentum is 0. So this is telling us what the final momentum is. And it's the same for each of them, right? The left-hand side is the same. And so if I just label this as P final, I would see P final is equal to something that doesn't depend on the mass of the cart in this situation. So the momentum is the same in this case, equal to. Okay, so there's nothing profound going on there. It's just that you're either dividing out the m or not. Any questions on that one? Definitely wasn't unanimous, but I think it's pretty easy to digest once you think about it. Suppose a ping pong ball and a bowling ball are rolling toward you. Both have the same momentum. I wonder what that looks like. And you exert the same force to stop each. How do the time intervals to stop them compare? So bowling ball and a ping pong ball, and they have the same momentum, and we push on them with the same force until they stop. How does the time interval compare? Let's see a vote on this one. Got to see what my vote is. I'm seeing A's and B's, probably more B's than A's, and I agree. They both take the same time here, and that's because the change, they're both going from the same starting momentum to 0 momentum, so their change in momentum is the same, and we're applying the same force. And again, this is the net force, but the other two forces cancel out. If they're rolling, there's a normal force and a weight force, and those are going to cancel out. So this net force really just reduces down to the force we're applying. Delta P is the same, F net is the same, and therefore delta T will be the same, the amount of time it takes between initial and final. Questions on that one? Okay, those are all pretty straightforward. This one's a little bit more complicated. We're going to consider 3 different situations. There's a ball flying through the air, and it's moving at a certain speed, and it's brought to rest. So let's imagine you're out in outer space, there's a ball flying, and I exert a force on it until I bring it to rest. Okay? Same situation, a different situation. Situation 2, the same ball starts out at rest, and we push on it until it's brought up to that same speed v. So we're talking about starting at speed v and brought to rest, starting at rest and brought up to that same speed v. And then 3 combines those together. We've got it going at speed v, bring it to rest, and then bring it back up to speed v in the other direction. And the question is, in which of those three cases is the object undergoing the largest magnitude change in momentum? The size of the change in momentum of it. And there are all sorts of combinations there. So you have to kind of think of the three and see, are any of them the same? And are those bigger than the other ones or what? All right, if you got a vote, hold it up. People aren't giving as many signs that they're ready to vote as before. I'm just going to try to gauge. I mean, they're sort of all over the map. Anybody want to try to explain their answer? I mean, I saw probably at least 5 different answers and multiple times. So.
I'm just thinking like the case of MB final, MB initial. In a first scenario, momentum would be negative. The second one would be positive, and the last one would probably be 0.
You mean the change in the momentum?
Yeah.
Right, because there's different momenta at different times, but you're saying the change in momentum. And so which one were you voting for? I didn't remember. D, which was 2. Okay. Yeah, so the first thing to point out is that we're talking about the magnitude of the change in momentum. So I don't care about the sign. So would you like to change your vote in light of that to probably B, I suppose, right? 1 and 2 are a tie, but 3 is 0. Anybody else want to talk on that one? That is the most common answer. It's not correct though. That's why I'm asking, is because it's most people think that that's true. Well, yes, but when we take the magnitude, we're sort of doing 1 and then adding it to 2, and so we could say the change in the change in momentum for 1, plus the change in momentum for 2. One of those may be negative, and one may be positive. We're going to add them together, and then if there's a minus sign, we'll just throw it out at the end. But we're going to add them together first. So if they add to 0, then we're out of luck. The surprising thing here is that they don't add to 0. 3 is actually the biggest change in momentum, and very few people have that intuition. So you're changing the momentum a lot. You're changing the momentum. Well, one way to think of it is with the impulse momentum theorem, right? If the ball is coming to rest and I'm pushing, let's suppose it's in outer space, right? There's a little rock coming towards me and I apply this force to it in that direction. What's the direction of the impulse I'm applying to the rock while I'm bringing it to rest? It's in the direction I'm pushing, right? Because there's the net force is in the direction, the only force is my hand, right? So the net force is in that direction. Impulse is net force times delta t. So the ball is coming in this direction. I'm delivering an impulse to it in that direction, right? Because I'm pushing in that direction. How about when I'm bringing it back up to speed? Which way am I delivering an impulse to it in that case? Same. So they add together. I give it double the impulse, and therefore there's double the change in momentum. That's another way. That's one way to see it. Another way to see it is just in terms of the momentum. Maybe we can take some simple numerical values to make it easy. I'm going to imagine, so here's my cases, oops, 1, 2, and 3 shown down there. So I'm imagining, the ball in case 1 is moving to the left, and I then bring it to 0 with my hand. In case 2, it starts out at 0, but I bring it to speed v going to the right. And then in case 3, it was moving to the left. I bring it to rest and then catapult it to the right afterwards, right? So that's sort of, and I'm just going to imagine, let's make the speeds 0 or 1 in magnitude, just to kind of do the calculation. So let's calculate what mv final minus mv initial is, x component. And that's the key thing. Momentum involves, it's a vector, right? So there's an x component, and I've got to calculate the x component, change in the x component of the momentum here. And x components have sign. So m times, and I'm going to take m equals 1, just to simplify my life. So forget about the m's. We're just doing v final minus v initial. V final is 0 minus v initial is -1, and therefore I get +1. We throw away the sign, and we still get +1. In this second case, v final is 1 minus v initial. V initial is 0, so that's change in momentum is 1. There's no sign to throw away. Third case, v final is 1. V initial is -1. When I subtract off v initial, I get 2. They add together. So, it's tempting to say, well, look, it was moving just as fast when it was moving to the left and when it was moving to the right. So there was no change at all. Well, yes, the direction matters when something is a vector. If it changes x direction, if its momentum is sort of its state of motion. And when I get it from going in this direction to the same speed in that direction, that's a big change in its state of motion, right? I've completely reversed it. So it corresponds to a large change in momentum. And we're going to use this kind of counterintuitive argument later on in some other voting questions to decide some things. But for most people, that's kind of counterintuitive. Oh, I was thinking, I forgot what I was going to compare it to. Compare it to kinetic energy, right? Kinetic energy, the change in kinetic energy in 3 would be 0, right? Because 1/2 mv squared, we're not keeping track of which way things are going. So 1/2 mv squared is the same in the final state and the initial state for 3. So you may be thinking about kinetic energy when you say, oh, there's 0 change in this case. But we're talking about momentum. It goes from a negative value to a positive value. And when the change is from a negative value to a positive value, that's a big change. That's not a 0 change, right? Or from a positive value to a negative value. Arthur, did you have another comment?
Yeah, I thought the initial speed was positive.
Well, so it doesn't matter which way you choose it. So are you saying you don't like this one having a negative x component? Is that what you're saying?
No, number 3.
So if I make this one +1, right, that would mean it's going to the right initially, and this one -1. The only difference is when you do the subtraction is you'll get a -2 in that case. And if we're talking about the magnitude of it, I would just say, throw away the minus sign. We just care how big it is. So, because you'll switch the sign of both x components if you change your axis. Okay, good. All right, we'll connect back with that later. Let's, I didn't bring any new worksheets for today, but we're chipping away at the worksheets that we had. We're going back to not the one that we used on Monday, but the one that we were probably using on Friday. It says impulse and momentum at the top of it. For you Zoom folks, if you don't have it in front of you, it's probably on Friday's date 1 week ago on the website. Anybody need a copy? I have a few extras here. And we've done problem 1 on here, but we're going to do problem 2, which is just forcing you to think about impulses and average forces, that kind of stuff. So a ball is bouncing off a hard horizontal floor. We're going to take plus y to be up so that we can talk about impulse y components and so on. Just before a bounce, it's moving down at 2 meters per second. During the bounce, the ball is in contact with the floor for 1/100th of a second, so it's a very quick bounce. And it goes up at a slightly lower speed when it leaves contact, 1.8 meters per second. Most bounces are like that. You lose a little bit of, goes up less fast than it came down, loses a little bit of energy on each bounce. And you're just supposed to think through what is the net y impulse component given to the ball during the bounce. Net means by all the forces acting on it. What about the gravitational force only? What about the floor force only? That's what we're asking. And there are also some questions on the back, but I'm going to try to give you enough time to think about A, B, and C at least. We can do D, E, and F together if we like. Just in case you want to check with me, in A, I get 1.14 Newton seconds. And in B, I get minus 0.029 Newton seconds. Okay, let's try to do the whole thing together. Most of you are looking like you're getting through the end of B at least. So we've got a ball bouncing on the floor. We're supposed to take plus y to be up. Let me just draw that in because we're asked about y components here. What is the net y impulse component given to the ball during the bounce? Well, that sounds like we're ready to use the impulse momentum theorem, right? mv final minus mv initial. We might say, I'm focusing on the ball, This is the impulse delivered, net impulse delivered to the ball, and it affects the change in the ball's momentum. That's how we're thinking of it here, right? So if I want to calculate the net y impulse given to the ball, I can just calculate its change in momentum. M is 0.3 kilograms. Let me just factor that out. V final, after the bounce is going up, that's a positive Vy final, right? And I should have put a little, because we're doing a y component here, we should have y components of the velocity up there. Vy final is positive. It's leaving at 1.8. Vy initial is negative. So we're going to have a minus a negative here. I think it was 2, right? Yeah. And when you simplify this number down, you get approximately 1.14. And I know it's not familiar yet, but impulse units, SI units, are Newton seconds. You can see that because impulse is force times delta T, newtons times seconds. Okay. Questions on A? All right, what about just the y impulse component delivered by the gravitational force to the ball during that same short amount of time that it's in contact with the floor? Well, here I can't use the net impulse. I need to calculate it more or less directly. I could say J from gravity, y, that's a big subscript. The y component of the impulse from gravity delivered to the ball is equal to, well, by definition, is equal to the average gravitational y force times delta T. That's the definition of what impulse is. It was the area under the F versus T curve, which is the average. Oh, and I should put an average over this little bar there. Okay, now for gravity, we don't really have to take an average because it's the same force. It's just mg the whole time, right? Gravity's y component is negative. Plus y is up. Gravity's pulling down on the ball the whole time during the contact. Pay no attention to the fact that the ball is moving from down to up. Gravity's pulling on it down the entire time. So this, no average needed. The y component is certainly negative. The mass is 0.3 kilograms. So that's just m times little g is this. And the delta T in seconds is 0.01, right? And so apparently that works out to minus 0.029 Newton seconds. I'm not getting it from that formula. It was our definition of what impulse was. We said, and you may remember that at one point, we were thinking of a baseball going off a wall, right? And we said, the force as a function of time looked like that. And we said, maybe the first contact is right there, and then it leaves contact right there. We defined the impulse to be the area under the force versus time curve because that seems like that was what affected how big of a change in the state of motion of the ball was. But since that's normally a calculus problem, we sort of took that area and smashed it while keeping the area the same into a rectangle. And if we call the amount of time for which the contact occurred delta T, the appropriate height to get the same area under the curve is the average force that's exerted. And that's true for X components, Y components, and Z components. So we said J, gravity, X component is by definition, F gravity, X times delta T. Same thing for Y components, same thing for Z components. That was the definition of what impulse was. The impulse momentum theorem is saying, hey, we defined what impulse was, and it happens to be equal to the change in momentum. So that's something different. This isn't a definition. It's sort of like if you had never heard of a force before, you might be forgiven if you asked, well, is a force just MA? No. Force isn't, it's kind of a miracle that force equals ma. That's like a big result that Newton found out. The definition of a force, well, it's something that we have a lot of intuition about, but it has to do with how hard you're pushing on things, and we have different force laws. But the fact that it equals ma is a big result. So that's the same thing here. The very definition of the impulse is the area under the F versus T curve, and we can calculate it as F average times delta T. Sometimes we'll calculate it that way. Sometimes we will be able to get the net impulse from the impulse momentum there. It's kind of like calculating the work done by a force versus using the work kinetic energy theorem to calculate the net work done by all forces, right? Sometimes we use Fx delta x, but sometimes we want the network or we want to use the network, we can just use the change in kinetic energy of the object. Okay, so that was B. How about C? C asks for the Y impulse delivered from the floor force. Now the floor force is complicated. Unlike gravity, the floor force is, well, we're starting right when it makes contact. It's almost zero because the ball hasn't compressed at all. And then the ball compresses more and more and more. The force gets bigger and bigger. And then it gets smaller and smaller and smaller. Its force versus time might look like this. And unlike with gravity, I have no idea how to calculate what the average is. For gravity, it was easy because when it doesn't change, the average is equal to the value it has the whole time. So how can we get the impulse delivered by the floor force to the ball during those 1/100th of a second? Yes. That's right. That's right. So, you know, the only dominant forces that are being exerted on the ball is gravity's pulling down and the floor is pushing up. What other forces are there if it's bouncing vertically? It's essentially, you know, mostly at rest when it's hitting the floor. So even if you were concerned about air resistance, it doesn't seem like a big force. So I think what Arthur's suggesting is that we could say the net impulse Y component is, by definition, net means from all forces. That's equal to the gravitational Y component impulse plus the floor force Y component impulse. And we just calculated these two, so we could do a little subtraction. We did the same kind of thing with kinetic energy, right? Where we said we dropped the ball from the top of a building. We calculated the net work done on the ball from the change in kinetic energy. We calculated the work done by gravity, and then we could back out the work done by air resistance, because that's a complicated force, but we can, since we already knew the other two, we could back it out. So I'm getting here, I'm just taking J net minus J by gravity. And when I subtract that off, it adds it on. So it's a number that's a little bit bigger than 1.14. Here we go. 1.17. Well, so this is very close to 0.03. So we add 0.03 onto this and we get 1.17. So this is 1.17 Newton seconds. Okay, questions on that? If it's not making sense, ask. I mean, the calculations aren't supposed to look amazingly difficult, but the concept of impulse, because we don't use that word in everyday life, just seems more obscure to most people. But you know, the work kinetic energy, change in kinetic energy theorem and the impulse change in momentum theorem are almost doing the same kind of things, except in one you have a delta x and the other one you have a delta t. Okay, so that's essentially what we just did. There are some things on the back and we'll just sort of go through those together. D asks, what's the average force Y component the floor exerts on the ball during the bounce? Well, we just found that its impulse delivered to the ball was 1.17, and its impulse by definition is the average force exerted times delta t. So if we know the impulse and we know the delta t, we can divide out to get the average floor force. Again, it's complicated because the floor force was essentially zero, then it got really big, and then it went down to zero again. So it's a non-trivial average that we're getting here without actually having to think about averaging anything else. So just dividing by delta t was 1/100th. When you divide by that, it multiplies it by 100. Okay. What y impulse component does the ball give to the floor? Okay, so here we're switching what is the impulse is being delivered to. Before we were concerned about impulses delivered to the ball. Now we're saying, hey, the ball is pushing on the floor. So it's delivering an impulse to Earth or to the floor, right? It's pushing on the entire Earth during the bounce. And the answer is, well, look, the force, Newton's third law says the force of the ball, of the floor on the ball is equal and opposite to the force of the ball on the floor. The delta t's are the same because it was in contact for the same amount of time. The average force is going to be the same because those forces, you know, when one is small, the other one's small. When one is big, the other one's big. They always balance each other out. The only thing that changes is the sign from Newton's third law, right? The ball gives a negative y component average force to the floor. And so the only thing that switches is the sign there for E. And then finally, what average force, y force component does the ball exert on the floor during the bounce? Well, we already found the y component average force that the floor exerts during the bounce on the ball. Here we want the ball on the floor. It's just the same thing with a minus sign, right? So I'm just forcing you to think about the vector nature of this, the fact that we're talking about y components here of forces, and the same thing is true for impulses. Impulse is a vector, momentum's a vector, so you've got to talk about components, and they can have signs that matter. Any more questions on that worksheet? That was some stuff I wanted to do with impulse momentum theorem. We talked about conservation of momentum, that, you know, if you have a bunch of things in a collision, the total momentum before equals the total momentum after. That was just a consequence of the impulse momentum theorem and the impulse approximation that says when two things have a contact collision like that, very quick contact collision, if you take from just before to just after the contact happens, any other forces just don't have enough time to give a significant impulse. So we're only going to consider the contact forces. This was the result. We also talked about certain types of collisions. We said when two objects collide, the easiest way to see that there's lots of different possibilities is if you have equal masses, opposite initial velocities. They might stick together. That's called a completely inelastic collision. They might not lose any energy, go off at the same speed that they came in with. That's called an elastic collision. And in between that, there are various kinds of inelastic collisions where maybe it goes out with just less speed than it came in with. That would be a generic inelastic collision, but not completely inelastic. And then strangely, sometimes, you know, some explosion goes off and they end up with more kinetic energy in the final state than they had in the initial state. That would be like something blowing into pieces, or they come in and it sets off a piece of explosive. Or you can think of chemicals sometimes, right? If a chemical is sort of unstable and it wants to split apart, sometimes something will knock it and make it unstable, and it will spontaneously split apart and release energy. So it's sort of like there was a compressed spring and it wants to be decompressed and it blows apart. That would be like an exothermic reaction for you chemistry folks. Okay, I threw some reading responses in the rest of this just to make contact with what you guys have been writing. When two railroad cars collide and stick together, what does the kinetic energy transfer into? So here we're talking about, I think, a completely inelastic collision. Two objects coming together, the two, you know, maybe the rest of the train and the one car, it sticks to it. Some lock closes, right? There was some extra kinetic energy maybe, and we're told that this is an inelastic collision and therefore it loses as much kinetic energy as possible, consistent with the conservation of momentum. Where does that kinetic energy go? Because several of you talked about, well, I know from my description in chemistry of, you know, when we have stuff, we're told that at the molecular level, everything is elastic, unless there's chemical transformations. But here, presumably, there's no chemical transformations going on. So where is that energy going? Easiest case is you have two cars that are with equal mass, opposite velocities. coming together, lots of kinetic energy, massive train car, and then they lock together and just sit still afterwards. So we lost a lot of kinetic energy. Where did it go? Yes, it released. Yeah, it's released as heat. It goes down very quickly to the microscopic scale, to the molecular scale. And so you're going to find where, you've probably seen something like this happen before. When that latch closes, there's some jiggling that happens. When that jiggling happens and some scraping that happens, right? It's not just going to immediately stop. There's going to be some jiggling that happens, and a lot of heat is generated there, and that comes out. We're not really losing kinetic energy. It's like, well, if I'm sloppy and I only pay attention to the macroscopic scale, it seems to disappear, but it didn't really disappear. If I could see the microscopic scale, I'd still see that thermal motion. Someone was talking about collisions happening in their chemistry class, collisions of gas molecules considered to be elastic. That's right. So when you have nitrogen molecules bouncing off of each other, they are elastic collisions, unless some chemical transformation is taking place. Okay, I'm slightly confused about conservation of total kinetic energy if one or more of the colliding objects loses mass during a collision. Okay, well, that's a different kind of thing if mass is being lost. We're not talking about two nitrogen molecules, coming together. We're talking about when they're far apart, there's no potential energy. They come together, they increase their potential energy because those electrons don't want to be close to each other, right, on the outside of the nitrogen atom. So they repel. The kinetic energy, yes, it goes down, but then after they're far away, it has about the same kinetic energy as it came in with once that potential energy is converted into kinetic. If you have mass being lost, I guess the easiest way to think about that is if you're ionizing some kind of molecule, right? So we got a molecule, it's got all its electrons here, something else comes in and knocks out an electron. It's lost a little bit of mass, not too much mass, but electrons have mass. Would it still be considered elastic? And the answer is usually no. If you take a chemical compound and you knock something off of it, those electrons are really stuck on to the nucleus, right? Because the nucleus is positively charged, the electrons are negative, and they're happy to be there. The same way, this ball is stuck way down here on the surface of Earth. If I want to get it off of Earth, I've got to do a lot of work to lift it really far away until the gravitational force goes to zero and it's somewhat free of Earth. Right? You have to do work. So you can imagine if something comes along, we want to knock this bit of mass off of Earth, and it's sort of like chemically bonded to Earth by the gravitational force, not the electric force. Something comes along and it pushes it up, and maybe it pushes it up so that by the time it is free of Earth's pull, it has hardly any kinetic energy left. Maybe it's just barely moving by the time it gets up there. So this doesn't have much kinetic energy left, and the thing that was coming in was losing speed as it pushed on this thing. That thing slowed it down. So there's an overall loss in kinetic energy. That's a kind of inelastic collision. And it has to do with because you're increasing the potential energy of the system. You've got some things that are stuck together. Those electrons are stuck to the protons like an invisible spring. And when you knock an electron off, you're stretching that spring. Or if you break a chemical bond, it's kind of the same way. It's not as long of a term force, but when you break a bond, you're actually having to put energy in to stretch it apart and break it. So yes, not all things at the molecular level are elastic. It's just if there's no chemical transmutations, then we usually think of them as elastic. Okay, we didn't talk about calculations involving elastic collisions, just for lack of time on Monday. But let's imagine that in this case, we got a 2 kilogram cart moving, that's this one, 3 meters per second, collides elastically with this 1 kilogram cart at rest. Find the final speed of the 2 carts. So no friction anywhere here. We're imagining that we're just told that it's an elastic collision. So that's telling us the kinetic energy before, which I can clearly calculate, is equal to the kinetic energy afterwards. And we also have conservation of momentum to work with. So we're going to have 2 equations, and we have 2 unknowns, right? What is the final speed velocity of this one, and what's the final velocity of this one? We can throw away the minus signs if we just want the speeds afterwards, okay? Now, I'm not going to go into great detail on this because the computations involved in doing elastic collisions are usually kind of ugly systems of two equations and two unknowns. But let's just think about it. Here it is. One's at rest, one comes in. Afterwards, generically, they both have different final velocities, and we want to find those final velocity x components. So I define an x-axis, and I say, well, one thing that's true is that x momentum is conserved from before until after. We work it out. One of them has 0 momentum to begin with, but that gives me an equation that has two unknowns in it because I want to know both final x velocities. And so I'm just going to have to hold on to that equation. But the other thing that we're told, because that word elastically is in here, is that kinetic energy is conserved. And this is kind of a difficult equation because it involves squares of variables. So we plug in the stuff having to do with this, what are the initial velocities and what are the masses? And then we get another equation in those same two variables. We got two equations and two unknowns. In principle, we can solve. In practice, it's a little bit ugly because we got squares in there, and that makes everything more complicated. The book shows that there's something about the relative velocities that just changes sign. I don't think I assigned any problems where you have to do this in the homework for chapter 7, which, by the way, is up and due sometime early-ish next week, maybe Tuesday, Monday or Tuesday, I can't remember. So take a look at it. We're essentially done with it now. Sure. All of this stuff is also in the videos that I post, and I say they're never required because they're really the same stuff we're covering in class, but I do a more careful job of covering them there, even though I'm not writing on the board at all. That was during the beginning of the pandemic when I made those videos. Okay, more reading response question. Is there an equation for inelastic collisions? Or why did the text only derive one for elastic collisions? Well, the idea is in elastic collisions, you have two things moving in the final state. So you have two unknowns, two final velocities. And at least if we're considering head-on collisions, so there's only one motion in one dimension, we have two unknown final velocity x components. So we need two equations, momentum and kinetic energy conservation, right? The elastic and conservation of momentum. In an inelastic collision, or at least in a completely inelastic collision, the things stick together and you've only got one object in the final state. And so you've only got one unknown. You only need one equation. Kinetic energy is not conserved, but momentum still conserved. So that's your one equation. There are cases in between which are just partially inelastic, and we'll consider that on the worksheet that we'll probably do next year. But before that, will we not encounter any inelastic collision problems or problems and examples and problems, or are they solved the same way as elastic collision problems? No, usually they're not solved the same way. If they're completely inelastic, it feels very different because there's only one unknown in the final state, whereas the elastic ones are quite a bit more complicated. But this is not, yes. So I think we did on Monday 1B and B1 before, but we didn't do B2, and there might be a B3 too. And rather than having you do it because the time is short now, I just want to go through the solution to this. So recall, we've got a hockey puck moving at 3 meters per second in the plus x direction. It's a very massive hockey puck. I also made up the curling stone math, so don't blame me for that. But in any case, in B here, the two don't stick together, but we're told the final velocity of the curling stone. And we were able to find out the final velocity of the puck by using conservation of momentum, right? Because in this case, we had two unknowns in the final state, but they weren't really both unknown. They gave us the curling stone's final velocity. So we only had one unknown. So we could use conservation of momentum to solve for it. Is it elastic? We're going to find out no. How much kinetic energy is gained or lost if it's not elastic, okay? If it were elastic, kinetic energy would be conserved. I know the initial velocities and I know the final velocities now. So I can calculate the total 1/2 mv squared in the initial state, the total 1/2 mv squared in the final state, subtract them and see if I get 0. If I get 0, it was elastic, right? If they're the same, it's elastic. If not, then it's inelastic. And so let's calculate the change in the kinetic energy from the final state to the initial state, or from the initial state to the final. So what change is final minus initial. And if the change is negative, that means we've lost some kinetic energy. If the change is positive, that means it's explosive. If the change is 0, that means it's elastic. So here in the final state, I've got a 1/2 mv, that's this -1 squared. I can just throw away the -1 because so 1/2 mv squared for the puck, 1/2 mv squared for the stone that was also moving at 1 meter per second. And then in the initial state, which I'm subtracting off, only one of them was moving. Only the puck was moving at 3 meters per second. When I do that subtraction, I say the change in kinetic energy from initial to final was negative. That means we lost kinetic energy. It went to a lower value there. And eventually, if it doesn't end up in thermal motion immediately, it very quickly ends up in thermal motion. Sometimes there's some oscillations that happen when things happen. These puck, they might vibrate for a small fraction of a second. And let's just finish up with this question here in the last minute. If the coefficient of kinetic friction between puck and ice is 0.1, how far from the collision point does the puck slide before coming to rest? This is just an old-fashioned problem here. I know the initial velocity. I want to know the delta x. So one way to do it is with the work kinetic energy theorem. We could also do kinematics and find out what A is. Well, no, I guess we don't have enough information to do kinematics here, but the work kinetic energy theorem, the puck is certainly a particle. So we can calculate the net work done on it, and we'll find out how that's going to be useful in just a second, is equal to the change in kinetic energy. With the results we just did, I can calculate that. And the net work I'm going to expand out as, well, first of all, the ice is doing negative work on the puck because it's pulling back opposite the direction it's going. We've got the coefficient of kinetic friction times the normal force, and the normal force balances out mg for the puck, right? So this is the kinetic friction x component, that's negative, times the distance it slides. That's fx times delta x. And that delta x, I'm calling d here, that's what we want to solve for. So solving for d, slides a 1/2 meter. Seems kind of ridiculous. For how fast was it moving? 1 meter per second. Only made it a 1/2 meter. That's kind of sad. Maybe this is ice probably doesn't have that friction coefficient, but I freely make up these numbers when I'm doing it. All right. Have a wonderful weekend. I will do my best to work on the exam grading, and let's hope that it gets done.